Alright, so there's one more issue we need to deal with in this particular chapter. I have drawn here a capacitor. And when we talk about a capacitor, you have to remember there's going to be charge or current flowing here. I'm going to start calling this IC, and you'll see why in a moment. But in between the plates, remember, there's no actual charge there. There's charge that comes from the power supply that creates excess charge on this plate, which then forces electrons off of this plate, which then flow through the wire. So there's no actual electrons flowing in between the plates. It's actually the electric force over here pushing the electrons off here, creating a positive charge. So if we go to apply Ampere's law, and Ampere's law states that the integral of B dot dl is equal to the magnetic constant times the current enclosed. So that means that whenever I draw a circle around here, the current enclosed is equal to IC. So IC is equal to the current enclosed. But if I draw a circle around here, the current enclosed is equal to 0, and that doesn't work. So we need to talk about how to deal with that. You can't have I enclosed equal to things along the path of a circuit. So we're going to explore and explain how we're going to deal with that. Alright, so as this capacitor charges, the electric field and thus the electric flux are increasing. So if we go back to, we're dealing with a parallel plate capacitor, we know charge is equal to the capacitance times the potential between the plates. And I drew a parallel plate capacitor, so we're going to talk about the electric constant over the area of the plate divided by the distance between the plates, and for the voltage we're going to plug in the electric field times the distance between the plates. Making use of the formula, the potential is equal to the integral of E dot dl. And that reduces down to, and this is the electric constant, but it's the electric constant that we used for dielectrics, times the electric field times the area. So this is essentially the electric constant, but the one for the dielectric, which includes the dielectric constant, times the electric flux. Alright, so now we're going to look at current, and we're talking about the displacement current, so that's the current going through the wire. It's going to equal the change in charge with respect to the time. And because this is Q, so we have to track all these equal signs, Q is equal to the electric constant times the electric flux, the derivative of that with respect to time can be written as such. So Q becomes the change in Q, which becomes the change in flux. Remember, the electric constant is a constant. Alright, so according to conservation of charge, IC should equal ID. So if we say the conductive current is equal to this, and this D stands for displacement, we're going to call the current, I'm putting it in quotes, I can't, the current that passes in between the plates is equal to the displacement current. So according to conservation of charge, those two things need to be equal to each other. So that means that the displacement current is also equal to the electric constant times the change in electric flux with respect to time. So this means that we need to rewrite Ampere's law as the integral of B dot dl is equal to our magnetic constant, the conductive current, plus the displacement current that is enclosed. So if we go back up here, when we do B dot dl around this circle, ID is equal to 0, and we have just the conductive current. And whenever we do B dot dl in between the plates, the conductive current is 0, and displacement current is the current that we're observing. So this means that a change in electric field gives rise to a magnetic field, which is actually observed in reality. So you can actually measure the magnetic field in between a capacitor plates as it charges. So the last thing we can talk about in this particular chapter is Maxwell's equations. And I've written Maxwell's equations down here. So we use the integral form in this course. There are derivative forms, but they often involve taking cross products with gradients, which we are not mathematically prepared for in this course. But as you look at these formulas, you notice that they look very familiar to you. The first two are Gauss's laws, the third one is Ampere's law, and the fourth one is Faraday's law. So Maxwell didn't actually invent the equations that are referred to as Maxwell's equations. He just put them together and fully understood their implications. And we'll discuss those a lot more in a couple weeks when we start chapter 32.